so. Yeah.
Sounds like it. All right, you ready?
Yeah.
All right, let's start with the last lecture of the day. Max will continue his discussion.
All right. So remember last time we continued our discussion of invertible gapped phases, and we saw kind of a general conjecture classification of such phases in arbitrary dimension, and also some examples in low dimensions. But last two lectures we were focusing just on phases with no symmetry. So now let's talk about enriching the physics with some global symmetries. So phases with symmetry. So first, let's ask what global symmetries are important in condensed matter physics. Okay, so electron number is conserved in condensed matter systems, so that's a U1 symmetry. Electron number. What else? Time reversal is a very fundamental symmetry. Unless you put on a magnetic field or take your system in contact with a ferromagnet, this is going to be a good symmetry. What else? Well, so these are kind of the best symmetries out there. Now there are some symmetries which are okay. So lattice symmetries. In condensed matter, we study solids. Solids, the ions form some crystalline arrangements. So there is we don't have the full, at least at high energies, we don't have the full translational and rotational symmetries, and we don't have Lorentz symmetries, but we have these symmetries of the crystalline lattice, and in 3 dimensions there are 230 different space groups. So various lattices that have different symmetries. So 230 space groups. In 3 plus 1D. So you can imagine it's a lot of fun you can have. Now, the reason I said that this is not as robust is that typically there will be disorder present in your systems, and disorder will break the symmetries of the lattice. But to a first approximation, we can still work with this. Another symmetry is SU2 spin rotations. Well, this is again only an approximate symmetry because of spin-orbit coupling and because, orbital rotations are broken by the lattice. But sometimes the spin-orbit coupling is weak, and then you have the spin rotations as an independent approximate symmetry. Okay, so now you can ask, well, is this it? Do we have any other symmetries that we should think about? And one comment I'd like to make is that oftentimes, even though these are kind of the symmetries out there at high energies, sometimes at low energies you have emergent symmetries. So it can happen. So 5 emergent symmetries, particularly near phase transitions. As a function of some parameter, it can happen that even though the microscopic symmetry governing your physics is some G, group G, it can happen that at the critical point you have some emergent symmetry G prime that's bigger than G. So for this reason, it's important to study kind of arbitrary symmetry groups. All right. So now let's talk kind of about terminology. So gapped. Remember, we're interested in gap phases. And without symmetry, remember we had two categories: intrinsic topological order, and invertible. When you add symmetries, generally this so there were different phases in each category depending on dimension, and when you add symmetry, these phases will generally split. So there are phases that are connected. There are states connected to each other in the absence of symmetry, but that are not connected in the presence of symmetry. So symmetry, symmetry G, you would have they can split in some way. Some of them are not compatible with symmetry. Say you have one of those systems with a gravitational Chern-Simons term in 2 + 1 dimensions we discussed last time. That's not compatible with time reversal symmetry. So some of these phases actually don't exist with symmetry. But okay. But in terms of terminology, so this split, and for intrinsic topological order, what we call these split phases are symmetry enriched topological phases. SET, symmetry enriched. Now for invertible phases, remember there was one invertible phase that was kind of boring but important, the so-called trivial phase. And in the presence of symmetry, this trivial phase will generally split up, and the phases that you get are so-called SPT phases. Symmetry protected topological. SPT. So SPT equal symmetry protected topological. So what that means is that if you have a non-trivial SPT phase, it means that in the presence of symmetry, you cannot connect it to a trivial SPT phase. So just as we had trivial invertible phases, we also have trivial SPT phases, which again the ground state is continuously connected to just a product. So in the same way we have this them here. And if you have a non-trivial SPT, non-trivial SPT, then as long as you have the symmetry present, you cannot continuously go between the trivial product state and the SPT without having a phase transition. But because by assumption, all of these SPTs descend from a trivial invertible phase, that means that if we allow ourselves to break symmetry, if we go back to this paradigm, then there should be some path taking us around this phase transition, but we break the symmetry. So symmetry, this vertical axis is symmetry breaking. Any questions? All right, so that's the nomenclature. Of course, what I haven't mentioned here is that in this bottom row, I assume that my symmetry group doesn't get spontaneously broken. So it's, of course, it's also possible that I have spontaneous symmetry breaking. That's another symmetry breaking. Symmetry breaking, and there are various patterns of symmetry breaking, and maybe I can have part of the symmetry being broken. So one can add that structure onto here, but let me not do that. So let me assume that whatever symmetry I'm thinking about, G, that it's not spontaneously broken, that it's fully preserved. Fully preserved. Yes. Okay. So we're going to focus now on these SPT phases, and what are going to be the interesting properties of these SPT phases? So let me just advertise, just like the non-trivial invertible phases had protected edge states, same with SPT phases. They'll have edge states which are protected as long as you have the symmetry. So SPTs have protected anomalous edge states protected by have, let me call it G protected anomalous edge states. And in fact, what you find is that for 1 plus 1D bulk, so let me write here bulk, 1 plus 1D bulk, the edge must be, the edge is just 0 plus 1 dimensional, and it turns out it must be gapless as long as you have the symmetry. If you have 2 plus 1D bulk, the 1 plus 1 dimensional edge is either gapless or spontaneously breaks the symmetry. In 0 dimensions you cannot have spontaneous, in 0 plus 1 you cannot have spontaneous symmetry breaking, but in 1 plus 1 you can, for at least for a discrete group, or gapless or spontaneous symmetry breaking. Those turn out to be the allowed possibilities. And if you have a 3 plus 1 dimensional bulk, then the 2 plus 1 dimensional surface can be gapless or spontaneous symmetry breaking, or sometimes there's a new possibility. There is intrinsic. Sometimes you can have symmetric gapped, but at the expense of having intrinsic topological order on the surface. So this is, and these are just like very broad brush things that one finds. In fact, there are kind of much more, for each SPT, there are much more precise constraints that are placed on the boundary by the bulk SPT, and kind of studying those constraints is very, very fruitful. Okay. Now, there is one technical. I've painted all this picture, but I didn't really tell you what kind of rules for symmetries we will consider. So remember we said that we are talking about systems on the lattice. So here what I want to stress is that throughout this whole discussion, we focus on so-called on-site symmetries. So remember, our Hilbert space is, by assumption, a tensor product of finite Hilbert spaces over some sites of the lattice. And what we assume now for the symmetry is that for each element G of the symmetry group, we assume that the action of the symmetry on the Hilbert space factorizes in this manner, where UI is the action of the symmetry group on each side of our Hilbert space, of our lattice, where on each side individually these operators have to satisfy So we'll call such symmetries on-site symmetries, and these are the symmetries that we consider throughout. Notice, strictly speaking, this excludes lattice symmetries, right? Like translation actually moves us, so it's not of this form. So these are kind of like internal symmetries. But turns out that a lot of magically or semi-magically, a lot of the stories that we'll have for these internal symmetries, internal on-site symmetries, actually extend to lattice symmetries as well, to crystalline symmetries. Just for the purpose of making, yeah, okay. So well, let me say one more thing. Why do we focus on on-site symmetries? Well, that's typically how all of these ones, other than lattice symmetries, are realized in condensed matter systems. But from your perspective, one can say that these on-site symmetries are the ones that can be consistently coupled to a gauge field. So on-site equals gaugeable, and that's very important. Yeah, we later on, maybe not this time, but next time we will actually explicitly see how to couple to gauge fields and why you need this. Okay. Now, for the purpose of these lectures, just for simplicity, let me focus on unitary symmetries only. So I'll not talk about time reversal, on unitary. And let me also focus on bosons, systems of bosons. So as a kind of prototypical example of a lattice symmetry that I'll consider is just a Z2 symmetry in a spin system. So I have spin 1/2 sitting on each side of my spin 1/2 on each side of my lattice, on each side, and the symmetry, the generator of Z2, simply acts by flipping all the spins. Okay. Questions? You can keep this in mind. All right. Yes?
Some more examples if not on-site?
We will see some examples later. Yeah. Uh-huh.
Can this representation on each site be a projective representation? Or
So
or is that the statement?
this is this statement, right? That on each side we assume that we have honest to God non-projective representation. Now, if you don't care about translational symmetry, then yeah, then most of the time we should be able to group sites together and build bigger sites on which we have, even if we start with projective symmetries on each side, on bigger, we should be able to build clusters on which we have faithful representations, and then we can just work with this. But we'll see projective symmetries come into the game just in a second.
Or can you not just pass to like a cover of the group? Like projective representations of the group correspond to honest representations of the cover often.
Right. So just to be very concrete, let's assume that we always work with faithful representations of whatever group we are interested in. Okay. So let's. But all these things about projective representations will come in just a second. So let's start simple. Let's start in 1+1 dimensions, where we will be able to construct some examples of, or guess some examples of SPT phases without doing too much work. and then we'll talk about kind of a general framework for generating many of these SPT phases in arbitrary dimensions. Okay. So 1 plus 1d SPTs of bosons. Okay, so our space is an interval, right? So assume I have some open chain, and we are saying that well, we want the bulk to be gapped, and we want it to be symmetric, and we want it to have unique ground state on a circle. Because SPTs come from a trivial invertible phase, but there can be some interesting physics going on the edges, and this interesting physics should be somehow protected by the symmetry. So we can think about maybe there is some low energy Hilbert space associated with the boundary degrees of freedom, and maybe the symmetry acts in some non-trivial way on that low energy boundary Hilbert space. Right? So remember, we had something very similar with our Majorana chain. Let's proceed by analogy with our Majorana chain. Remember, for the Majorana chain, we had the fermion parity symmetry fractionalized into two operators, gamma left and gamma right, acting on the left and right ends of the chain. And these were fermionic, so they anti-computed with -1 to the f, and that actually gave us the protected twofold degeneracy of the ground state on a segment. So maybe we can have something similar happening here for our internal global symmetry G. So maybe the action of symmetry G on this interval can split up into actions on the left and right ends, as long as we are in this kind of low energy sector. Guess U of G is equal to U left of G, U right of G on low-lying states associated with the boundary. Where again U left and U right will be localized at the left end and right end. And they can have exponentially decaying tails, but that's okay. Okay, but now we know that overall our U should satisfy the group law. We know that U of G times U of H should be equal to U of GH. So that means that U left of G times U right of G times U left of H times U right of H should be equal to U left of GH times U right of GH, at least on these low-lying states. Okay, so that means that U left inverse of GH, U left of G, U left of H should be equal to U right of GH u right inverse of h u right inverse of g u right of gh. I've used the fact that the operators left and right commute, right, because they are spatially separated. I hope I'd have this in the right order. Okay, so now this is some operator acting on the left end of the chain. This is some operator acting on the right end of the chain. So for them to equal, each one of them has to be proportional to a constant. And since these are unitary operators by assumption, this just has to be some phase. Let's call that omega gh, which is a phase. All right, so that means that individually the symmetry, the effective symmetry action on the left end satisfies the group law only up to a phase. U left of G, U left of H is equal to WGH, U left of GH. So it means that this is now that this is a projective representation. Projective representation. And the operators on the right end will have the same relations, but with W inverse. Okay, but now if you look at this relation, there are some consistency conditions that W must satisfy. Because if you think about product of 3 operators like this, well, there is associativity, right? I can group it like this, or I can group it like this. And I can use these relations twice on each end, and that will give me some consistency conditions that W must satisfy. And in fact, the consistency condition I'll find is that what I call dW of GHK is equal to, so this is by definition WHK WGHK WGHK WGH. This must be equal to 1 for this associativity to hold. All right, so W must satisfy this this non-trivial relationship. What else? The other point is that, well, really, I'm decomposing the action of U on my system into actions on the left end and the right end. But nothing prevents me from multiplying this by some phase and multiplying this by some opposite phase. So U for each G, U left for each G is defined only up to a phase. So what happens to W if I change these phases? Let me multiply by some nu of G here. I don't know if this is a good name. Maybe I should call this mu instead. And U right of G to U right of G mu inverse of G, where mu is just a complex phase. Mu of G complex phase. Okay, so you can check that the way we define W under this procedure, it changes into W of GH times nu of G times nu of H over nu of GH. So W is only defined, W of GH is only defined up to this ambiguity. So this defines projective representation, or more precisely, projective representation more precisely, we say that W is an element of the second cohomology group of G with coefficients in U1. And if you haven't seen this notation before, we will define what we mean by this for any dimension n in just a second. All right. But before we talk about this formalism, for now, just take the definition as this condition must be satisfied, and W is defined up to this ambiguity. And let's see what the consequences are for the boundary. So let's suppose that we have a W such that we can never turn it into a 1 by multiplying by such phases. Suppose we have a kind of honest-to-God projective representation. Well, that will imply that the boundary must be degenerate, that the boundary must be gapless. If W is non-trivial, a boundary must be gapless. Must be gapless. Why? Well, our Hamiltonian must commute with the symmetry U, but because of this factorization by arguments very similar to the ones that I gave for the Kitaev chain, it must also commute with both the left piece and the right piece. Okay, so that means that my eigenstates must be a representation of this. Must form a representation of this projective representation of the symmetry group, and we know that projective representations always have dimension larger than 1. Or, in other words, suppose you had a unique ground state, right? Then under the action of each symmetry, you would have to have, it would have to go into itself up to a phase. So you can check that this would imply that WGH is equal to mu of G, mu of H over mu of GH. That is, W would be trivial. Okay. Right, so whenever W is non-trivial, boundary is gapless. There's a very famous example of a system, of a Hamiltonian that has this property. And that's the Haldane chain. We will shortly construct exactly solvable examples for any group G, but let me begin by telling you about an example that's not exactly solvable, but which is both historically and also to a certain extent experimentally important. Example, Haldane chain. So this is a chain of spin 1s. with antiferromagnetic interactions. Spin 1, right? So on each side of the chain, I have spin 1s sitting, so three sides, three states. Symmetry group G, so this has a symmetry G equal to SO3. Turns out that this Hamiltonian, when you look at it on a ring, is fully gapped. Gapped bulk. But if you look on a chain, on an open chain, then you find a fourfold degeneracy. And the fourfold degeneracy is associated with the fact that this U of G, U left of G, is a projective representation. It's actually a spin 1/2 representation. So then effectively you have a spin 1/2 degree of freedom emerging at each boundary. And you don't need the full SO3 symmetry. You can, for instance, break this down to Z2 cross Z2, and this ends will still survive. So if you don't like thinking about continuous groups, you can also think about discrete groups. Okay. Any questions? Okay. So we kind of guessed, right? We guessed that there should be such 1 plus 1 dimensional SPT phases with these properties, and turns out that this object, this algebraic object that we defined here, fully classifies 1 plus 1D SPT phases of bosons. Okay, so that's nice, but there are several questions. First of all, can we construct some exactly solvable examples where we can check all of this? Second question, is there a bulk characterization? Can I see that something is an SPT without looking on its edge, just by looking on some closed manifold, a space-time manifold perhaps? What about higher dimensions, right? This is just in 1 plus 1D. Right. So turns out that there is a very large class of examples that we'll now describe, which are known as the cohomology construction, where you can answer all of these questions. And they really go back to the paper by Dijkgraaf and Witten. So Dijkgraaf, Witten, cohomology construction. Kind of the relevance of these two SPT phases in general dimensions was realized by Chen, Gu, and Wen around, I'd like to say, 2011, 2012. Okay, so let me tell you what this does for you. So this gives a large set, gives a large set of boson SPTs in any dimension D. In fact, for unitary groups, for unitary G, gives all boson SPTs in dimension up to 4. And they're classified by an algebraic object that we already alluded to, which is group cohomology. So that's a completely algebraic object that we'll define in a second. All right. So our next objective will be to introduce these models, which will turn out to be exactly solvable, and to study their properties. Questions? All right. So we will formulate these models, at least initially, in terms of a partition function. We will later discuss, or might discuss, how to write down Hamiltonians. But for now, we will work with we will write down a path integral, or partition function on manifold M. So we are trying to build a model with symmetry G. So we'll focus on G. Focus on G discrete. You can at least formally do this for continuous G as well, but let me stick to discrete G. So we want to build a partition function of the theory on manifold M, and let's begin with M closed. Begin with M closed, and I'll specify my manifold M by giving its triangulation. So I'll build it as a simplicial complex. It will turn out that the simplicial structure that I specify doesn't affect the partition function. But to define the model, let me start with some simplicial structure. So here I've taken part of my two-dimensional manifold and I've broken it up into simplices, two simplices in this case. So pick simplicial decomposition. Further, we will need to choose a branching structure. Choose a branching structure. What branching structure means, it means local ordering of the vertices. Right? So if I look locally, I can say which vertex, I can enumerate the vertices in some ascending order, and I put arrows on links from smaller vertex to larger vertex. Right? So say this is vertex 0, this is 1, this is 2, then I'll draw arrows like this. And the point is that these arrows never form loops because of the ordering. Okay. So then, if I look at so we're in d dimensions. Here I drew d equal to. So the simplices, each simplex will be a d simplex, so it will have d plus 1 vertices. Which I list from the smallest to the largest, right? This is the branching structure allows me to do that. And then I have to look at that. Then for each of those simplices, there is an orientation. right? And I can say whether the orientation is +1 or -1 relative to this ordering of the vertices. So for instance, if here I take my orientation to be out of the plane, then this simplex, for instance, will have orientation +1. And if we have some, for this one, if the arrows go this way, if the branching structure goes this way, then the orientation of this simplex is -1. That's right? Yes. Okay, so there is an orientation. So this, let's call this delta D. There is an orientation S of delta D. Okay. Very good. So this is the machinery that we'll need.
M is orientable, the same orientation.
Yes. Let's assume that M on a manifold or with orientation. Remember we said that we will focus on symmetries which are unitary. So then that means I don't have time reversal symmetry. That tells me that I don't really know how to put the system on a non-orientable manifold. But this can be generalized to non-orientable manifold. Okay. So let's see. So my model will be defined on this manifold, and on each vertex of the manifold, I'll put a group variable G, group element G. Put G I in G on each vertex V I. Okay, so let me define the partition function then in the following way. Z is 1 over number of elements in G to the power of number of vertices, and then I sum over my group elements on each vertex, and there is the action, and let me tell you what the action is. The action is just a phase. And this phase is obtained in the following way. I look at every D simplex in my decomposition, right? So in this case, I would look at every triangle. And on each triangle, I do the following. I look at the vertices in ascending order, and I look at group elements on each one of those vertices, G up to the last vertex, and I raise this to the power. And I take some object nu, which is going to be a phase, and I raise that to the power of the orientation. And this nu is going to be an element of group cohomology that is really the main input into the construction. So at this point, I must really tell you what this group cohomology is. No getting away from it. But first, let me ask, how many people have seen a simplicial cohomology? Okay, so I'm going to assume that everyone has seen it. If you haven't seen it, just open Hatcher and we won't really need it. But so how many people have seen group cohomology? Okay. So let me define group cohomology. I think it's about half of the. So group cohomology let's define, and I'll be working with group cohomology with elements with coefficients in U1, but you can do it for an arbitrary group. So let me define a homogeneous cochain of dimension n in the following way. It's just a function of n plus 1 group elements. So f is just a function of n plus 1 group elements taking values in U1 with and it has to be a symmetric function in the following sense, with f of g g0, g g1 up to g gn equal to f of g0, g1 up to gn. I can turn these functions into a group simply with the multiplication, law being just multiplication, and right. And now, most importantly, let's define the differential let's define df so there's going to be a function c n g u1 to c tilde n plus 1 g u1. Let's call that function d, defined in the following way: df g0 g1. So df has to depend on n plus 2 variables plus 1 f of g0 g1 up to gi. So the ith element we remove here. So this already looks a lot like simplicial cohomology. So there is a nice way to visualize this, which is let's say f belongs to, say f is a homogeneous 2 cochain, right? So it's a function of 3 group variables. So let me think of these group variables as sitting on triangles as they were, for our manifold. So then f is defined on each triangle, and then df, well, will depend on 4 group elements. So I can kind of think of df as living on, so f lives here, and df is kind of defined on a tetrahedron. G1, G2, G3, 0. Right, so they are ordered. They have a branching structure. Right, so df of G0, G1, G2, G3, I can think about it as looking at the faces of this tetrahedron with their correct orientation and just reading off the f on each face. Right, so first face I remove G0, so I get face formed by G1, G2, G3. So this would be, and that face is oriented outside, so that's good. F of G1, G2, G3, right? So this is this skinny phase here. Then second phase, I remove G2, I get this phase G0, G1. Second phase, I remove G1, I get this phase here behind, and that phase is oriented inward, so I put the -1 orientation, G0, G2, G3, etc. For the remaining two phases, I get F. Okay, so it's really the connection to the simplicial cohomology is now very clear. Questions? Yes?
Sometimes isn't the definition of this exterior derivative of group cohomology given by this, but then for the endpoints, instead of removing just G0, say, or Gn plus 1, one does something special where one takes basically G0 times the next element, for example, G0 times...
So the question was that there is a different definition, and this is the difference between homogeneous cochains and inhomogeneous cochains, and we'll talk about inhomogeneous cochains in just a second. So that's one point. Another point is that sometimes you can have non-trivial action of the symmetry group on the coefficients, and then there is also a twist to the story, but here we are just thinking about the simplest case with no action of the group on the coefficients. Other questions? Now, so we have this group CNs, and we have maps D between them, and it turns out that if you do D twice, you get 0. So if you have C tilde n minus 1, C tilde n, C tilde n plus 1, right? I have these maps D n minus 1, D n. And the point is that dn times dn minus 1 is equal to 0. I guess with elements in U1 it means it's equal to 1. But okay, let's just write in additive notation. Okay, so then let me define Hn GU1 as kernel of dn over image of dn minus 1. Right, so I want all, in other words, I want all f's that for which d is equal to, df is equal to 1, but f cannot be written as d of something else. Usual cohomology type story. Now, returning to the question that was asked, actually all of this cohomology is non-trivial because we require this property. Otherwise, we could always, everything would always be d of something else. And this, you can say, well, why? There's clearly some redundancy in these f's because they have to have this property. So maybe I can just get rid of one of the elements and just, yeah. So that's how you define the inhomogeneous cocycle, which we will also need. Sometimes it's usually people work with these inhomogeneous cocycles. Sometimes homogeneous ones are also useful. So let me introduce both. So here, homogeneous So inhomogeneous cocycle W. Did I put tildes here? I think I want. I have tildes everywhere. Good. So the inhomogeneous co-chain CNGU1. This will be just a function of n group variables. And it's related to the homogeneous cocycle in the following way: G1, G1, G2, G1, G2, G3, up to G1, G2, Gn. Right, so we kind of kill that redundancy, and you can also go the other way around. F of G0, G1, Gn is W of G0 inverse G1, G1 inverse G2, up to Gn inverse Gn. Yes. All right. So how do we think about this? You know, there is a similar graphical picture for this for this inhomogeneous cocycles or cochains in this case, which is that now we are going to put group variables on the lengths of the of our simplices, and we are going to make sure that this you can kind of think of them as a gauge field on these simplices, and we are going to make sure that the gauge field is flat, right? So G1 times G2 is same as G1 G2, and we'll talk about interpretation in terms of the gauge field probably already next lecture, but yeah. Okay. So then, how do we translate this D operation from the homogeneous case to the inhomogeneous case? Well, so there is going to be a D W, which will belong to Cn plus 1 of GU1, defined in the following way. So W will depend on n plus 1 group variables. And there is a painful definition, but the picture is actually kind of nice. So now in the ith location, instead of just removing the element, we take gi times gi plus 1, and then we continue as normal. And then the last element is okay, sorry this is so tedious, but one just has to suffer through it. Okay, how does it we will need this. How does it look? how does it look? Right, so again, let's just draw the case of n equal to 2, and D takes us to 3 cochains. So now W lives on this 2 simplices with kind of flat gauge fields on the boundaries, and DW will live on 3 simplices, 0, 1, 2, 3, where the way you put the elements is from 0 to 1 you put G1, from 1 to 2 you put G2, from 2 to 3 you put G3. Right, so dW of G1, G2, G3. And on the rest of the edges, you just make things flat. So you make sure that things are flat. So this will be, for instance, G2, G3. This will be G1, G1, G2. And this one will be G1, G2, G3, I guess. Is that right? G1, G2. Okay, so now when you define DW, you do kind of the same thing that you did here. You look at this. You look at this 3 simplex now, and you just look at a W on each face. And W on each face depends on the group elements on the edges of that face. So you just, let's say, when we remove vertex 0, we get this simplex 1, 2, 3, and the group elements on the links of that simplex are G2 and G3. So we get W, G2, G3. What about if we remove 1? We get 0, 2, 3. What are the group elements? They're on the edges. There are G1, G2, and G3. So G1, G2, G3, W, and then we could just do the same for the other 2 faces. All right, this is what we get. And remember, this is exactly the kind of expression that we got when we were talking about our projective representations. So, okay, that's encouraging. Okay, so now we define both homogeneous cocycles and inhomogeneous cocycles. Since we just translated things over, D squared is again 0, and you define the cohomology as taking kernel over image. So, okay. I think we have all the technology that we need, and we have 5 more minutes. So, let's see. How far can we get with this technology? So this new depends on G at the vertices of the d-dimensional simplex. So this is going to be an homogeneous cocycle. So we take nu to be a homogeneous cocycle. That means that this theory is going to have a symmetry when I multiply all the elements by some group element G. So symmetry, all the Gi going to some G naught times Gi, where G naught is an element of G. Okay, so that's a kind of obviously going to translate into some nice on-site symmetry action if we go to the Hamiltonian language. Okay, so this is the symmetry, right? We are talking about symmetry-protected topological phases, so whatever our theory, it better have the symmetry. Okay, now there is the following interesting statement that on a closed manifold, if M is closed, then for any configuration G, e to the minus s of G is going to be equal to 1. And that means that, well, I sum up a bunch of 1s over all possible values of G's on the vertices. I'll just get that G to the number of vertices. So that means that the partition function on a closed manifold is always going to be 1. You might be very disappointed. This is a very boring theory. Its partition function is always 1. But this is actually what we want, right? Because in the absence of symmetry, we want this to be a trivial invertible phase. And the partition function of a trivial invertible phase on any closed manifold is 1. Okay, so maybe things are not so bad. How do we prove this property? Proof. Okay, so suppose I have some manifold M. Let's say M is a sphere. Doesn't really matter. So I have its triangulation into, I don't know, a bunch of triangles. I want to compute this action, e to the minus s of G. Let me do this by adding one more vertex, G, let's call it G infinity. And let's connect all the vertices to this one vertex. Yes? Now, I would like to make the following statement. Whenever we have any triangulation in any dimension with group elements on the vertices of that triangulation, then this nu is defined on D simplices of the triangulation, and it defines a cocycle in the simplicial sense. You can just use the definition of D nu to check that nu defines a D cocycle in simplicial sense, right? So nu is something that's going to be defined once I fix the group elements. Nu is going to be something that's defined on every D simplex, and then by taking then D nu of that is going to be defined on every D plus 1 simplex, and by the virtue of the fact that nu is a homogeneous group cocycle, that's going to be closed. So nu defines a D cocycle in simplicial sense. That is, D nu is equal to 1 in simplicial sense. So now let's do this. So I've added this single vertex to kind of so now for every D simplex that I had, I'm going to have D plus 1 simplices, right? So here I had triangles. They become, I can build tetrahedra out of them. And now let me think about product of D nu over each one of these tetrahedra. right? Well, by the Stokes theorem, let me put in the correct orientations. By the Stokes theorem, if I integrate d of something over some d plus 1 simplices, that's the same as product over d simplices on the boundary of nu. Well, this is e to the minus s on the right. D nu is 1. So this, product over each d plus 1 simplex, products over each tetrahedron is, d nu on each tetrahedron is 1, so this is 1. Right? So if you think about it, the pieces of d nu on this faces connected to g infinity, they all cancel. All right. So this proves that the partition function on any closed manifold is equal to 1. And I guess we are out of time, so let's stop here. Any questions? So next time we'll talk about wave functions, how to write down ground state wave functions for this model. We'll talk about what happens on the boundary. We'll see that we can kind of build an effective theory for the boundary, but the symmetry will act on that boundary in a non-on-site way. And then we'll talk about coupling this to a flat gauge field, and we'll see that the partition function in the presence of a non-trivial background gauge field will no longer be 1, and that will be a way to detect non-triviality of this SPT. And if we have time, we'll talk about lattice Hamiltonians as well. Any questions?
Just a quick math question. So you defined your group cohomology sort of built on the simplicial one. If I give you other ways of thinking about the cohomology, like CW or check cohomology, for example, check. If I give you just a bunch of the combinatorics of the intersections of open covers, is there a similar analogous way to build the group cohomology starting from that description?
So good.
I mean, I understand this is very physical. It comes from the lattice, so it's great. But practically, the other cohomologies are way easier to work with than simplicial cohomology. So since this is built on simplicial cohomology, I'm just curious whether there's...
You can do several things. So first of all, I mean, this is the group cohomology itself, right? Is just some algebraic object. So you can define it with no geometry in mind. Now, if you want to kind of use geometry, what you can do is you can think of these objects as you can think about this classifying space BG, and you can think about nus as cocycles on BG. So that's a more topological way of thinking about them. And then every gauge bundle on the manifold is a map from the manifold to BG, and then you can pull back the cocycles and get the partition functions. Yeah. But it's
really curious. I mean, these kind of these explicit formulas that you get when you give me a simplicial decomposition of the manifold, then you have a concrete formula for what you mean by it. If I give you a CW complex instead, is there an analogous formula?
Well, I think then this is perhaps the simplest way to think about it in that case. I don't know if mathematicians in the audience have something more to say. Maybe Anya. So.
I just want, given another description, I mean, here you do something to the geometry. You triangulate the geometry, and then you can build, you can give a concrete definition for what you mean by D and everything for the group cohomology. If instead I give you an open cover, let's say I'm doing check cohomology instead, so I just give you a bunch of open covers, and I tell you about the combinatorics of intersections of the open covers. Starting from there, can I do this? Or if I give you a CW complex instead?
I'm confused. Are you trying to get a way to compute the group cohomology, or to understand the map from N?
No, just to compute the group cohomology.
Well, so there's a space called PG, which is the
Okay, fine.
So with that space, you can compute whichever way you want. But you can also do it much easier. Like group cohomology, you can compute from completely algebraic terms.
other questions? Okay, see you tomorrow.
Like there's a dumb thing you could do with check homology. You can go from check to a simplicial picture somehow. So that you could do. But I was more curious of the CW case, because that lets you sort of talk about things in a much more degenerate but compact way, as far as covering the manifold, as far as describing the geometry is concerned. And then, I mean, you're using simplicial homology as in these examples, a crutch for computing the group cohomology instead of doing it more abstract.
No. I mean, I'm just defining the simplicial, the group cohomology I'm defining in a completely algebraic way, right? I'm just using these pictures as a way to kind of visualize it, right? The group cohomology is just defined as some
formula, right? Like the formula for the D.
Yeah. So
this is something which.
this is completely algebraic, right? There is no.
True. Yeah.
Now you can ask, okay, if you have a W, how do you integrate W over the manifold?
Right.
And I think that's the question
That's a question.
you are asking.
Right.
But then, yeah, in general, okay, so you want, I mean, it really only becomes interesting if you have gauge fields on the manifold, right? In this case, the partition function is always, so let's put on gauge fields, right? So then you have to, you have to define the gauge fields, so they, the transition functions between patches, and I think you want to define a cocycle, a D cocycle using check cohomology from those transition functions.
Yeah, for check, I think it's very close to this.
Well,
check is a slightly more efficient way of talking about simplicial cohomology, because you just define the, if you have good intersections for the open covers, they're just kind of building a simplicial decomposition.
Yeah, you can just maybe, I don't know, but you might run into trouble because you can have more intersections. So it's not.
But I'm saying it wouldn't surprise me if it's easy for check. CW is much more extreme, right? Because you get these much more, but also you get much more efficient coverings of the. Yeah, I'm just asking. It's a practical question. Like when you try to figure it out with a gauge field and so on some manifold, do you end up sort of triangulating the manifold somehow to do the computation or not?
Oftentimes in the simple cases, what will happen is that I think we can go offline. Let's do that.